Hi, everybody. Thank you for coming to my talk. I start by thanking the organizer for inviting me to this important conference. I would have loved to be in Budapest in person and meet you and see the old friends that I know in Budapest in person, but unfortunately, due to unforeseen circumstances, I could not make it in person, so hence we will do it by video conferencing this time, reserving the pleasure of seeing you in person for another occasion. So my talk today will hopefully convince you that certain biological catalysts, such as ATP synthase, may have functions beyond their recognized biological role as a biological catalyst. In this case, you will see that they influence not only the rate of the reaction they are supposed to catalyze, but also its delta G. In other words, the actual energetics of the reaction is influenced by this enzyme due to its electric field, in fact. So here is the plan of my talk. I will just start by reminding the audience with some very basics behind this work. Then we'll describe the scientific hypothesis that drives the research. And then we'll talk about the results. And I cannot give a talk like this without touching upon the contentious issue of the hot mitochondrion paradox in a few slides, if time allows. And then we'll close by a few general results. So the basics here, first of all, we are zooming in on the mitochondrion, which is, as most of you, or probably all of you know very well, that the mitochondrion is the powerhouse of the cell in the sense that it produces the ATP that we need in order to carry out our living functions, a term that was coined way back then in the 50s by Philip Siekevitz in a very well-known scientific American journal article. Mitochondrion is composed of two membranes, one that is outer and smooth, and the inner one is corrugated, as you can see, with the so-called cristae, which are these invaginators, these folds that you can see here in this figure. And there is, so by having two membranes, you have essentially three compartments. The compartments on the outside here, a compartment in between the two membranes, and an inner compartment that is called the mitochondrial matrix. The inner compartment, which is the matrix, is essentially where the reaction of the Krebs cycle happen. And when these reactions happen, here is another figure that is more schematic of the two membranes here. Here's the outer part is on the north of this figure, and the matrix is on the bottom here, and in the middle here is the intermembrane compartment, or intermembrane space as sometimes it is known. So when we eat the food is converted into these highly reduced cofactor NADH and FADH2 that are delivering their electrons and the associated protons to the complexes of the inner mitochondrial membrane. And given that the reactions that happen in the inner mitochondrial membrane, the so-called electron transport chain reactions, are a set of concatenated exergonic reactions, and hence the energy that is released, the free energy that is released from these reactions, is used to push the protons against the chemical and electrical gradient, so that the concentration of the protons in the intermembrane space is much higher than that in the matrix. Then the protons will migrate and go through a special channel in the enzyme that is the subject of my talk, which is the ATP synthase, such that every proton that enters from the intermembrane space side to the gap to the matrix through a little pore in the FO unit, as it is called, of that enzyme, experiences a downhill travel, a downhill through the potential energy surface. In other words, It's composed, of course, of an electrical part and a concentration part. And when that happens, the energy is captured through a rotatory mechanism to fix inorganic phosphate over adenosine diphosphate to create ATP that we use in order to fuel all the processes of life that are otherwise non-spontaneous. So to give some texture to this, here we have another view of this, of the double membrane structure, whereby here there are violet arrows that are superposed on the figure to symbolize the electric field that is generated by this proton imbalance. So if you look at the energy terms of that govern this setup, you will have that these two terms, a chemical delta G term and an electrical delta G term. The chemical term can be converted into a delta pH term, since the imbalance in concentration is here describing an imbalance in protons, and of course minus the logarithm of the activity of the protons is pH, so you can easily convert that one into a pH a pH gradient, and the other one is converted into free energy as well, using the Faraday constant, and N here symbolizes the number of protons that are being transmitted or transferred from one compartment to the other, and delta psi is the voltage difference between the two sides of the inner mitochondrial membrane. To give some numbers, typical delta pH is around, here is about 0.8, 0.91 pH unit. The voltage difference is approximately 200, 300, 180 millivolts, so 0.2 volts, let's say in round numbers. The distance is 100 angstroms, round numbers as well, and hence the electric field here can be anywhere between the 10 to the 7, 10 to the 8 volts per meter, which is very, very strong compared to anything you can achieve in a lab, for example. So the Mitchell theory that I just described received a Nobel Prize in '78, and then Boyer and Walker received their Nobel Prize in 1997 for the elucidation of the enzymatic mechanism underlying this ATPase function. So the scientific hypothesis driving this work, the structure of the enzyme can be captured into this diagrammatic form here on the right, whereby you have essentially a cylindrical part called FO unit for oligomycin. The O in FO refers to oligomycin because this is the inhibitor of that part of the enzyme. You have a stator that holds the structure together. You have an axle around which the lower part rotates with respect to the top part, and so essentially it's a rotatory mechanism here, whereby the rotatory mechanism changes the three-dimensional structure of the enzyme pockets at the bottom here, through which the catalysis occurs. Now, since this is essentially a cylindrical part and consists of alpha helices, the reasoning was such that since these are alpha helices, and we all know from our undergraduate biochemistry courses that alpha helices have a strong dipole moment due to the addition, the vectorial addition of the local dipole moments associated with the NH-O carbon bonds along the side of the helix. The hypothesis here is that whether the imbalance generated field, as shown here in the violet by the violet arrows, may or may not be reinforced by a local field generated by the structure of the enzyme itself, and as we've seen, that could be likely due to the alpha helical structure of the FO unit. So you can have two scenarios, whether you have a Z component, let's call the perpendicular axis on the membrane the Z axis. So we might have a Z component of the protein, let's call it ATPase electric field against the proton imbalance field or with it. And in either case, if the magnitudes are comparable, then there will be a net effect of that additive or destructive. So in the first case, the resultant here is less than the original field of the proton imbalance, while in the other case, you can't see the arrow here because of my video, but the arrow here is much longer or much greater because of the constructive interference between these two fields. So the question was, would there be perhaps an extra term in Mitchell's formula that is this one, the textbook formula here, this formula? That's the hypothesis that we're trying to test in this work. So in other words, does it end here? Or do we have an extra term that is related to ATP synthase's field? ATP synthase is sometimes also known as ATPase if it works backwards. So we want to test if there is such a term, whether it is a positive or a negative, a constructive or destructive term that could be added to the potential formula here. So if we summarize it more symbolically, like if we have delta G of the process, it has a chemical component and an electrical component, but maybe also an ATPase or ATP synthase dependent component. That is the question. So here's some of the results that we have found recently, and that ATP synthase is a moonlighting enzyme, and the word moonlighting is actually a technical word. In English, it means that if I am moonlighting, it means I have a secondary job whereby I'm trying to improve my income through that job. Now here, ATP synthase, in fact, as you shall see in a moment, does have such a moonlighting job. And this is, by the way, is a technical term in biochemistry. So the work has been featured on the cover of ChemComm, which obviously was very pleasant to us. These are the the scientists that produced the work. We have Jean-Nicolas Vigneau, Fahimi, Maximilian Ebert, Yuji Cheng, Connor Tannahill, Paul Muir, and Professor Nguyen-Dang here. So the method, the approach that we've used, we have first selected 5 of the best structures that were available for the enzyme, and here are the references. And the structures happen to be well diversified in terms of the nature of the organism. We have bacteria, yeast, fungus, we have mammalian, we have another bacterium. So there is a variety of organism, and also the structures were solved by a variety of methods here, whereby we have X-ray and electron transmission microscopy. So, and these are some of the data, the characteristics of the experiments. So what we've done, we've taken these structures and we have uploaded them in the Adaptive Poisson-Boltzmann solver, APBS server, to generate cubes of molecular electrostatic potential that correspond to these structures. After making some basic assumptions about the structure, first we had to clean the structure by adding the missing hydrogens and the missing residues or heavy atoms. Then we have used amber force field in order to approximate the charge density of the protein. And we have set up some basic parameters as shown here, the pH, the temperature, the dielectric constant, etc. And a monovalent counter-ion concentration that is characteristic of mitochondria that were found in the literature. And then an in-house Python code was written in order to analyze the cube of the molecular electrostatic potential that were generated by the APBS server. So the results that I'm going to show you include the following. First of all, before showing you the results, let me give you the summary. I want to first establish a z-axis as the long axis of the protein, along which we are going to section the protein perpendicularly to that z-axis, and then look at the electrostatic potential in the planes as we cut through the z-axis. So you can see on the figure on the right here that the most important positions in this work that we're interested in is the position, excuse me, whereby the proton just enters the pore and where it just exits the pore here in the matrix. Because this is the difference in the potential between these two positions will constitute the term that will be added to the Mitchell theorem, the Mitchell formula, the third term of the equation that we propose to add. So if you notice here, it is the potential is basically red. That is a code for positive potential. And here it's mainly blue, which code for negative potential. So there is indeed, this is just the big summary of the movie you're just about to see. So what you're going to see is as we chop down the z-axis, different sections, like salami sectioning the protein, we will notice the change in the color of the field as we go down, and we are looking from above. So here's the potential surface at position z is equal to minus 21 angstrom means we are up in the gap here between the two membranes. When you reach 0 is here, and when you reach 70, you just exited from there, from the FO unit to get into the matrix. So these are the two key points, 0 and 70. So let's watch. As we approach, so we're still here in the minus, so we're still in the gap. Oops, we just entered the proteins, still red. So this is in the membrane. All this is the part in the membrane. And when we reach 70, we just exit. The proton will just exit into the matrix. Here we go. It turned into blue. And after that, we didn't analyze in detail the rest because that might be a subject for future studies. It's not directly relevant to this work as far as we think. So this is the F1 unit below here. You can see it's all blue down below. Here we finished, the protein is finished, and then we're in the deep waters here in the matrix. So how do we summarize this? Let's say we take this section. Then we will want one number that summarizes what we're seeing. So we are going to pixelate this figure, and then except at the region around the protein, we give it 5 angstrom around the protein exclusion region, but everything out there will be average up to a certain limit here, because the charge distribution in the protein is not accurate to be described by point charges, but we do not think that that's a limitation far away from the protein. So we start at about 5 angstrom from the protein and average all these pixels, the value of the electrostatic potential out there. And here's what we get. So this is 0, below 0 means you're still in the gap. And then from 0 to 70 here is within the FO unit, as you can see here. And then the proton exits at about 70-ish in this region here. And then we didn't analyze this part in detail, but here is the result still. But what we can see that at the moment of the point where the proton enters, there is a big spike in the potential, a positive spike. In other words, it kind of acts like a potential barrier against the entry of the protons into the FO unit. And then there are some fluctuations here, and then when it exits, there is a definitive difference in potential between the entry and the exit. Now, there is much more to the story that I'm going to skip for the sake of time, but for instance, here, these are the different organisms. They all follow the same trends, all the 5 organisms that we analyzed. Whether we take the average over the entire sector, the entire 360 degrees sections, or we divide it into, let's say, 10 sectors. So this is one organism, but we only averaged over these slices, 10 slices per section. And you see that the behavior is independent of the direction upon which we average. So that seems to indicate a generality of what we have found. So the conclusion of this part is that we can assign 3 separate but complementary roles to ATP synthase. The first role is the well-known textbook putative role, whereby it is a catalyst, it's a biological catalyst, and hence reducing the delta G double dagger of the reaction of phosphorylation of ADP into ATP and water. The 2 others are new and are described in this paper that we have just published. So the 2 discoveries, what we have discovered here is a novel role, and that is the role of altering the delta G of the reaction of translocation of the protons. This is the term that we have added to the Mitchell equation. As in here, it influenced the energy of translocation of the protons. Furthermore, we have also discovered, and this, by the way, is quite significant because, if we convert from millivolts into delta G's numbers, here maybe it's not very impressive that it is 3 or 5 kilocalorie per mole in these organisms, and, much lesser even here. But we have to remember that we did all this solvated in water, but in reality, the FO unit is solvated in lipid, in the phospholipid bilayer, and hence the dielectric constant is no longer around 80 or 78 or 79. It's more like 2 to 3, and that will change dramatically these numbers. So these are lower bound. This is the bottom line, and you can see that the bottom line, in terms of millivolts, is like the 10th of the orders of magnitude sometimes of the natural electric field. So the natural potential voltage. So in other words, it's quite important, at least according to these calculations. Now, in terms of the barrier that I indicated at the beginning, that the ATP synthase appears to create a potential energy barrier that regulates the rate of proton translocation itself. So in other words, the protons, when they come near the pore where they have to enter, they first face a barrier. So in other words, the ATP synthase's potential, electrostatic potential, appear to operate like a gatekeeper that regulates which protons are allowed to enter into the pore and which protons are excluded from entering. And it selects those protons that are the highest proton in terms of kinetic energy, thermal energy. In other words, the high end of the tail of the Maxwell-Boltzmann distribution of the protons. That's fundamental knowledge at the moment of great interest, I think. The work was deemed of sufficient importance for a journalist to capture it in this news article in Chemistry World, and we were really excited about that. So the last thing I have to touch upon a little bit is the hot mitochondrion paradox, since that's the topic, since the mitochondrion is the focus of this work. And these may not be unrelated topics. So in 2018, Pierre Rustin and others, Dominique Chrétien, published this very intriguing paper indicated that based on their fluorimetric measurements of the temperature of the mitochondrion, that the mitochondrion might be about 10 or more degrees hotter than its immediate environment in the cell. Well, that was very surprising, because 10 degrees might not seem like a big number, but when you are imagining that this is over distances in the nanometer space scale or length scale, then that becomes very significant. The gradient would be tremendous, enormous. So no wonder that some people were skeptical. And the steady state theory predicted actually that the maximum you can get over these distances that is consistent with the parameters that describe biological material would be something like 10 to the minus 5 degrees Kelvin, not 10 degrees Kelvin. So you have 1 million-fold disagreement between the theory of the steady state calculation and between what seems to have been experimentally observed. So that created a lot of fuss in the literature and much debate. And as we tried to resolve this a little bit, so with the help of a brilliant undergraduate student at the time and now PhD student, Mohammed Nasr, and collaborators at the Ukrainian Academy of Science and at Dalhousie University and at Zuwail City of Science and Technology in Egypt, with these collaborators, we have collected a circumstantial case that actually shows that mitochondrion might indeed be hot for several reasons from the literature, from what was known already. So there is every indication that there might be a hotter mitochondrion, but in that paper we haven't said by how much. How much hotter? So here came my colleague Payman Fahimi at Université Laval in Quebec, and we, Fahimi and I have formulated a hypothesis that reconciles this enormous disagreement, showing that both sides are right, but for the different reasons. So Fahimi's theory essentially is centered upon the fact that protons in biology do not wander around unattached. You don't have proton wandering around in the biological system. It is a hydrated hydronium ion. So first you need that hydronium ion to cross the ATP synthase needs to be dehydrated first. Then the hydronium ion has to be deprotonated into water and proton, because molecular dynamic simulation have shown that the proton crosses the ATP synthase's FO unit as a proton and not as a hydrated hydronium ion, or not even a non-hydrated hydronium ion. So you need to desolvate, deprotonate, allow the proton to pass, and then when it gets to the other side, you have to reverse the movie. You have to run the movie in reverse. You have to, the moment it exits, it will meet the first water molecule and create hydronium ion, and immediately the solvent around will reorganize its structure so that to solvate that. So you have an endergonic operation on one side and an exergonic operation on another side. On the other side, they more or less almost cancel. So in doing that, when the proton exits, there is these operations happen on a very short time scale in the picosecond range. And this is why we propose the following idea. We propose that in this is the last figure of the talk. Here you have the temperature that we calculated in our through our hypothesis, and this is the time scale here. And it is known that ATP synthase accepts 1 proton per millisecond, roughly. Here is like each a little bit less than a millisecond. It's like 1,200 protons per second. So you have a spike, but that time scale is too long to show the structure of the spike. If you spread this by several orders of magnitude into the picosecond time scale here, then you start to see the structure of the spike looking like that, more like this two waves of heat production, in other words, that can be translated into temperature. So what happens is that you have very short-lived temperature spikes. And because of the very large number of the ATP synthases, fraction of an Avogadro number, then it gives you the illusion of a continuous signal, while it is not continuous. It is a bunch of spikes of temperature events. So in other words, the mitochondrion is hot, it seems, and both the theoreticians and the experimentalists are correct, but you cannot use steady-state theory as the theoreticians have done. And of course, if you average our spikes, you get the theoretical value more or less, and if you don't, you get the order of magnitude of the 10 degrees here. 7 is close enough, given the uncertainty in the parameters. So there may really not be 10 to the 5 gap, as it is known, after all. So at the end, I would like to thank my collaborators listed here and the extended, present, and former members of my group. And I also would like to thank all these organizations and universities and funding agencies that help fund the work. And at the end, I thank you very much.